Concentration of hydrogen, these brackets mean concentration. Concentration means the amount of moles of solute stuff being dissolved, divided by the number of liters of solvent, the stuff doing the dissolving. So capital M we use to symbolize moles per liter, and you're going to see that a lot. Concentration of hydroxide, and then pH, and we're going to get into what that means momentarily. This is all based upon Arrhenius' ideas of the amount of water that breaks down into hydrogen and hydroxide ions that we've talked about before. This is the equation that we looked at. The hydrogen ion part is the acid, the hydroxide part is the base. But the key to this is this double arrow shape, and that's what we're going to be looking at here. So let's do that right now. Arrhenius found that water did not break down completely, so it was considered to be both a weak acid and a weak base, which is kind of odd. But there's a handful of compounds that we are familiar with that will actually have that breakdown. So we have even number of hydrogen hydroxide ions in solution. That's called amphoteric solution. That's not important. This is what we call an equilibrium equation. An equilibrium equation says that you have certain quantities of both the reactants, the products in the solution, because this does not break down completely, in fact, hardly at all. There's going to be a little bit of this, a little bit of this, and a lot of this in the container. And the amounts of material is going to be constant under consistent conditions, like same temperature, pressure, and quantity of material. So because of that constancy, shall we say, we come up with a constant mathematical equation in which we take the products and divide by the reactants. The concentration of all the products divided by the concentration of all the reactants. And like I said, the brackets mean concentration in moles per liter. And this is called a K expression. K is short for constant in German, which begins with the letter K. So we put the products, which are the hydrogen ions and the hydroxide ions, in brackets over the reactants, which is H2O, in the denominator. The problem is we can only have aqueous and gases in this expression. So the H2O cannot be in there, so that gets kicked out of there. So now we have K equals concentration of hydrogen times the concentration of hydroxide, and Arrhenius identified that as K sub W, where W is, of course, water. And there is a value for that, and that value is 1 times 10 to the negative 14. And what that says is no matter how acidic or how basic your solution is, you're still going to have a little bit of the other in there. It has to, because of the water that is dissolving it. And so this is the equation that we're going to be using a lot of in this section and any other sections dealing with pHs and concentration. I think we got one more after this. So let's take a situation where we have a 0.001 mole per liter hydrobromic acid solution. And because hydrobromic acid is one of the 7 strong acids, this is going to be a single arrow breakdown, complete dissociation. You start with 0.001 here, and because of the stoichiometry of 1 to 1 to 1, everything has the same coefficient. Then we're going to have 0.001 here and 0.001 here, but we're going to have nothing left here because it is broken down completely, so that just disappears. So all we're going to focus on is the hydrogen and the bromide, in a sense. But really all we care about is the hydrogen, because it's in water with hydroxide. So the bromide is just kind of there. It's what we call a spectator ion. Doesn't do anything, but we just know how much we have of it because of the hydrogen. But the concentration of hydrogen is 0.001 moles per liter. So we're trying to find the hydroxide concentration in that. We simply take the equation 1 times 10 to the negative 14 equals H positive times OH negative, and substitute 0.001 for the hydrogen, and then divide both sides by that 0.001, and we get hydroxide is equal to 1 times 10 to the negative 11 moles per liter. So, that's how that works. Now, if we have neutral or pure water, now, when I say pure water, I'm not talking about the garbage that's in the tap water. And it's not the garbage that's being sold as bottled water, like Aquafina or Dasani or whatever it is. That stuff is just tap water itself. But we say that pure water has a pH of 7. The question is why? Where did that number come from? And I'm about to explain that to you. The pH of the bottled water that you get is like pH of 5, which is why some people, like myself, gets heartburn if I drink too much of that bottled water. Regardless, if it's a neutral solution where it's pure water, it's equal concentrations of hydrogen hydroxide. That's what makes it neutral. So we know, according to Arrhenius, that 1 times 10 to the negative 14 equals the product of those two. But if they are equal to each other, we'll just use x as an unknown value. So that's going to be x and that's going to be x, so it's going to be x times x, which is x squared. So we have x squared equals 1 times 10 to the negative 14. To get x, you take the square root of both sides. And that x now, which is the concentration of hydrogen and hydroxide, but we're going to talk about hydrogen right now, is going to be 1 times 7 times 10 to the negative 7 moles per liter. All right? So, now, here's the issue with that. Scientists have found that the general public is not the most knowledgeable group of people in the world outside the scientific community. You tell them something is 1 times 10 to the negative 7 moles per liter, they've either fallen asleep or their eyes are rolling, or they're checking their phone, they're not paying any attention to you whatsoever. So they decided to come up with a way that maybe is much more representative of something that they can grasp. It may not actually be what they think it is, but at least it gives them an idea. So they said, well, let's take the logarithm. Now, logarithm, if you're in Algebra 2, if you had logarithms, logarithm is another name for exponent. And log, like that, is base 10, and the logarithm, or the exponent of base 10 is negative 7. So the log of that is negative 7. Now, here's another thing that the general public hates. Negative numbers. They hate fractions. They hate negative numbers. We don't have any fractions here, but boy, we got negative numbers. And they said, well, we're going to have to change that too. So instead of taking the logarithm of 1 times 10 to the negative 7, they take the negative logarithm of 1 times 10 to the negative 7, and you have 7. Ooh, I like 7. 7 sounds so positive. It is positive, isn't it? I like 7. That's nice. But here's the thing about that. Negative log is a mathematical process. And that process begins with the letter P. So that's a little p, meaning negative log. The concentration of hydrogen is H. It's the H of pH. pH is the negative log of H positive. And since in neutral solutions, the concentration of hydrogen is 1 times 10 to the negative 7, the negative log of that is 7. That's where they get the neutral pH from. It's from Arrhenius. So, remember that time you took logarithm, you were doing logarithm, you went, this is stupid, what am I going to use this for? Yeah. Alright, so let's take an example that I gave you in the script. We have a 0.100 molar KOH solution. We want to know what is the concentration of hydrogen, hydroxide, and the pH. All three of them. So, KOH is one of the strong bases, so it breaks down completely. We don't have to write out the dissolving reaction like we talked about before. We just put down 0.100 molar. We know that's what it's going to be. That means then that the concentration of hydrogen times that 0.100 is going to be equal to 1 times 10 to the negative 4. So the concentration of hydrogen, when you divide both sides by 0.100, turns out to be 1 times 10 to the negative 13. And again, the label moles per liter anytime you deal with the concentration. Hopefully you're doing this in your calculator, kind of get used to dealing with your calculator stuff. Then, and this is, I strongly advise you doing your practice your calculator on this if you have not done anything with negative logs before. So negative log, parenthesis 1 times 10 to the negative 13 close parenthesis, will give you an answer of 13. And that makes sense because 13 is basic. It's greater than 7. If it had been less than 7, it would be an acidic solution. Greater than 13 is a basic solution. KOH, big OH on the end. Strong base, lots of hydroxides. Yes, Bob. All right, next one. Next example, we have a 2.25 times 10 to the negative 4 mole per liter solution of LiOH. Now, why would I do that? Because most of the time, you don't know what the pH is. You don't know what the concentration is. You have to go figure it out and all that. And life is not full of nice, neat numbers like 1 and 3 and 10, all that stuff. No, it's ugly stuff like this. So again, we got a strong base. LiOH is a strong base, but now we want hydroxide, hydrogen, pH. Okay? Because it's strong, we know that the concentration of hydroxide is this quantity right there. So we've answered question number 1. Bing! Question number 2, what is the hydrogen ion concentration? This is where the Arrhenius equation for Kw comes in. 1 times 10 to the negative 14 equals 2.25 times 10 to the negative 4 times OH. Or H positive rather. Because that is OH. So, I don't know why I have that in there. That's kind of confusing. So I'll cross that out. But anyway, you take 1 times 10 to the negative 14 divided by 2.25 times 10 to the negative 4. You get 4.44 times 10 to the negative 11 moles per liter. Alright, so that goes right there. And then the pH is the negative log of the H. Be careful of that. People tend to get confused. They say they usually take the first number they have and plug it in there. It's got to be H. It can't be OH in there for that. So this is negative log of 4.4 times 10 to the negative 11. Punch that you calculate, round it off to 2 decimal places, please. I want 2 decimal places for all my pHs, 10.35. I realize the first one I only gave 13, but technically it should have been 13.00. All right, so it probably takes about 10 minutes to get all the way to the front page. We shall see here any minute now. Any minute now. I just got, oh look, it almost showed up. We got one more page to go back and stare at this thing as it sits there and says, no, I'm not going to do it. I'm just going to be a pain in the butt and make you wait. Okay, that's nice. So now we go down to the bottom. Oh, well, I guess it was the other page. That makes sense. What a maroon. So it's on this page where we have the practice problem, the end of the whole discussion there. And so let's do that again. Let's go over here. And practice problems. I want you to find the H, OH, and pH of these 5 problems. You know, the problems the board doesn't want me to show for whatever reason. But it's, oh gosh, okay. So anyway, it's on the end of the script. Have fun.